So hello everyone, it's great to be with you today and being able to present our work, which includes some innovation work we have been doing in partnering with the European Space Agency and particularly for the rail sector. So I will start with the contents of this presentation, which is what I describe as a great infrastructure challenge. Then I will present how space technology can be used for addressing these challenges. And also, I will talk to you through some work we have been doing using satellite technology for developing susceptibility assessment to geohazards, including landslides, expansive clay, sinkholes, and how using AI we have developed this technology that can be applied for the whole networks. So let's start with the great infrastructure challenge. So we have the aging of the infrastructure with the majority of it being more than 70 years old. We have the heavier use of the infrastructure than ever before, not only in terms of traffic of our roads and rails, but also due to the increase of the world population, we have settlement of population into hazardous areas. There's also climate change that impacts the condition of our infrastructure and the declining budgets of the managing agencies that have to monitor and manage all this infrastructure. And on top of that, we have the shortage in labor skill, especially in engineering and globally. So for all these reasons, it's becoming more and more important to find effective and efficient ways of managing these challenges. So let's look at some numbers in terms of the economic impact of these geohazards. So let's start with coastal erosion. So I have some numbers here. It's an estimated cost of $500 million per year in US alone. We have landslides costing about $880 million per year globally. Sinkholes an approximate $300 million per year in US alone. And clay subsidence, it's costing an enormous $12 billion per year globally. And not only we have this huge economic impact, but geohazards are going to continue increasing due to climate change, according to World Bank reports and from what we've heard from other presenters today. So what is the problem? The problem is that geohazards can occur anywhere globally, and it's really, really difficult to be able to monitor thousands of kilometers of roads and rails or whole cities. And maintenance is in most cases reactive, so that makes it a lot more expensive than proactive measures. And also climate change resilience is low. So how does climate change impact road and rail networks? Some examples include the intensive rainfall, which impacts the earthworks along the rail corridor, causing landslips, as well as the expansive clays, causing more changes in the behavior in terms of seasonality. We also have the severe droughts in the similar way, causing severe shrinkage of the clays affecting the corridors. So the question is, how can space technology be used to help addressing these challenges? So how it can be used is to be able to characterize the ground behavior and the response of the ground according to the extreme weather events. So how does the ground react to an extensive and intensive rainfall or drought phenomena? So what I'm going to show you is some examples where we have developed soil moisture algorithm for being able to measure using satellite technology the soil moisture as well as the ground and infrastructure displacements. So having information about the ground soil moisture and the ground displacement is a very good information for characterizing the condition of the infrastructure. And I will also show how we use space technology for developing susceptibility assessment to geohazards. And the great advantage of that for the susceptibility to geohazards is that using space technology, you are able to update the information regularly to reflect any newly triggered landslides, for example. While if you have traditional, conventional landslide inventory maps, especially at country level, this is done every few years because it's really, really difficult. So using space technology, we are able to have a more dynamic approach. So we're able to update these geohazard maps regularly to be able to react to these changes. So this is an example of a railway network monitoring the displacement. So I'm just presenting some of the displacement work. So you can see in these locations here that you can identify problematic locations. So in that way, you can monitor large areas remotely. That's another example where you can see the railway identified very, very clearly because of its backscattering characteristics. So in that way, you can monitor, again, huge areas in one single analysis, and you can distinguish areas that are problematic, shown here in red and orange colors as opposed to the green section. So in that way, you can prioritize the maintenance in a better way and allocate resources. So you can concentrate more onto the areas that are problematic, and in that way, you also reduce the carbon footprint. So for each individual location, then you can get more information, such as the location, how much is moving, the changes in the behavior of the ground in graphical and tabular format, as well as comparing with, let's say, a point that is moving versus a point that is stable. And this is another example where we can see here an area that's been suffering from increased subsidence. So ground displacement can be measured both historically as well as with updated information, and early warnings are also in place where you can identify locations that have exceeded the set thresholds. So this is very important here because you can see in this area here, we had no movement up to about this time. And then we can see something that has triggered the increased movement in this location here for this specific point. So with advanced post-processing, we can identify even those locations that have changed behavior at some point, because it's a point, it's a location which had no problems before, but something has triggered a change in the behavior. So now I'm moving to something else, which is condition assessment of the railway using space technology. So what we can see here with white color is the railway section shown very clearly. So using space technology, we can monitor the condition of the railway with every satellite pass. So in this example, we can see clearly the railway line, all white, in a different dates, exactly the same thing, so nothing is obstructing our railway line. While in this example here, what we can see is that in this location here, something has obstructed the railway line. So not only visually, but also graphically, we can demonstrate that. And in that way, in an automated way, we can set early warnings or alarms that something has changed in the behavior of the railway. And in this specific example, that's due to sand accumulation. And this is from an example where we implemented this technology. So you can see that this is a railway line going, it's on a coastal area. So you can see different shades here of gray. So the darker the gray color, the more severe the problem is. So we can see that at this specific location, we have a very dark color here, and we can see a drop in the signal of our satellite here. And if we want to look at the optical image for that specific location, we can see that the railway is affected by sand accumulation during that specific date. But it can be done on a time series basis, where with every satellite pass, we're able to monitor whether any change has happened compared to the previous data. And moving to vegetation. So vegetation is also a problem, could be a problem for the railway. So we can measure the density and coverage of vegetation along the rail corridor with every satellite pass. And again, if set thresholds are exceeded, then we can identify that. So this is a close view of part of the railway corridor. So we can see here the darker the green color is, the more dense vegetation is. So nothing is happening here, but there is vegetation in these locations. And if we look at the optical image, we can see increased vegetation on these locations that they shown before from the image analysis. And let's talk a little bit about the soil moisture algorithm we have developed at GeoFem in partnership with the European Space Agency. So using soil moisture data from in situ sensors from more than 49 countries, using data that span over a 3-year period, and this is so that we capture the seasonality. We have developed this algorithm that, if we can see here the algorithm results versus the in situ soil moisture results, we can see a very good correlation in excess of 0.8. And for that, we use, as I said, satellite data from different sources. It is a very complicated algorithm because you have to account for different parameters. But it's global, so it can be applied globally. We have tested it in different countries with very good results. So instead of having only the in situ sensors, that allows to have global coverage even in locations where you don't have in situ sensors installed. And let's look at a practical example where we applied this. This is from an example in Singapore. So in this case, the client wanted to monitor historically and also updated the soil moisture data for this area here. So this is the output of the soil moisture algorithm. So we get the soil moisture data at the pixel level, and this is volumetric soil moisture content estimate. So you can see light color here because we have small values of the soil moisture content. This is an image that was analyzed on 20th of February, 2023. And near this area, there was a meteorological station. So we're able to actually see the rainfall in that area. So 20th of February, we are here. Not much rain happened before. But if we compare it with a few days later, so moving from 20th of February to 16th of March, we can see an increase in the soil moisture content, so much darker color here. And if we look at our rainfall station nearby, we can see that there was a lot of rain a few days before. And let's see how it is applied on the rails. So we have applied this along a railway section, so you can see here the soil moisture values along this distance during the dry season and during the wet season. So showing a clear difference in the soil moisture content. And also what we can see here, which is, I find this very interesting, is we can detect patches of poor drainage. So the white color here identifies increased soil moisture content. And if we look at the different dates, the values of the soil moisture content, we can see that at this exact location, we have increased soil moisture content values. And this is important because this could be an indicator for failed track drainage or ballast fouling. And moving now to the susceptibility assessment to geohazards. So it's what I call satellite data meets engineering insight. So using information from satellites like the displacement data I just showed you, the soil moisture data, topographical data, geological information, asset damage data, ground truth data, and a lot of other information. And using AI, we are able to assess the susceptibility to geohazards like landslides, swelling clays, and sinkholes, giving them a score. And the most important thing, as I said, these are able to be updated regularly to reflect any changes. So this is an example. So you can see here in dark red color, we have high susceptibility areas, moderate in orange, low and no susceptibility. So you can overlay this map over your entire rail network in cases where, even at the stage before you design your railway, to select the best routes of your railway, or when you have your railway, to see which areas are at higher susceptibility. And this is an example where this was recently applied in California. And here is a comparison. This is our model. So as I said, we are using the parameters that are the most important in the occurrence of landslides, using also satellite technology, and compare this with the Californian Geological Survey map. So in our model, we use training and validation, but not satellite data was not used in all of the area because this is hundreds and hundreds of kilometers. So we estimated the correlation, we determined the correlation between the different parameters and then applied our developed algorithm to a much bigger area. So that in that way, it's a lot more efficient. But we can see very good correlation. So you can see no susceptibility in this central area, increased susceptibility in this area, and here. And we have also developed something similar for the expansive clays. So the darker the red color, the higher the severity is for susceptibility to expansive clays. So the great thing about this is that you have a very good spatial resolution of your expansive clays maps, but also you can update that to reflect, it's very dynamic, to reflect any drought period you have or any period of heavy rainfall. And these are some proof of what I just showed you. So this is the score, this is a severity score. So something went wrong with the presentation, sorry. So this is from a white color, which means very low severity. This one here shows some seasonality in the data. So this comes from a light pink color, while this one has highest score out of all. So it's at higher susceptibility score, higher severity, because it has stronger seasonality and also downward movement. And this is a correlation between the ground movement and the soil moisture content, only from satellite data. So you can see here, this is a displacement, and this is a volumetric soil moisture content in black. So you can see how they correlate well together with the subsidence followed by the uplift seasonally. So this is an example of using this correlation. We use use it in our models in order to be able to identify the susceptibility of this. So before the conclusions, I wanted to say that this is a technology that is advancing a lot due to launching of new satellites all the time from European Space Agency, NASA. We have different types of data, optical, radar, penetrating cloud. So it's a technology that is advancing a lot. Also, a lot of commercial companies now have launched new satellites, improved spatial resolution. We also have cloud computing now that is able to process a huge amount of data very quickly, and the use of AI, of course. So due to all these reasons, I believe that this is going to be, we will see more and more applications, I would say, also in the infrastructure sector. So to conclude, the space technology allows regular network-wide infrastructure monitoring, which allows earlier identification of issues. So you can go retrospectively and you can identify issues early on. That's a key, I think, aspect, because it allows you to take measures before it's too late, before a collapse. In that way, it's more proactive maintenance is allowed, and it enables building resilience to climate change. And some of these that I showed you now have been applied already to some rail examples. So thank you very much.
Thank you. We've got an opportunity for questions again. So, as before, if anybody's got some particular questions they'd like to tease out while you've got the expert in the room, please put your hand up. We've got one question here.
Hi, Spencer Cook from Sistra. That was really interesting. So for smaller railways, would you need a geostationary satellite to get real-time data? So
the data is near real time. So if it was real time, it would be even better. But it's near real time, but as it is at the moment, you get updated information every few days. So temporal resolution is really important to address these issues, but I think it's progressing in that direction. So that's very good.
Oh, thank you. Thank you.
Front row.
Angus McGregor, Balm Ritchies. Does cloud cover affect the resolution of the data?
Cloud.
Cloud.
Okay.
If you can't see between the satellite and the ground, what happens?
Okay. Good question. So when you have optical data, like we're all used to Google Maps and everything, then cloud is affecting. But in the examples I showed you, cloud is not affecting because it's radar data, which penetrate the clouds because it works in microwaves. So for all these examples, no, the cloud is not a problem.
Good question.
Yes.
Anybody that's not in the front two rows have questions? We're being inclusive. Whilst you're thinking, I had one.
Yes.
When you think about some of the monitoring and some more traditional methods, is it significantly more expensive or similar if you're trying to come up with a satellite-based solution?
That's a very good question, because when people hear space technology, they always assume that it's really expensive. But actually, it's not. I would say it's more economical. Of course, each case is different, but it's more economical because of the characteristics. You can cover huge areas with one single analysis. So it works complementary to in situ instrumentation, but it's more economical. Yes.
Thank you. David was working on transparent route upgrade. This isn't applicable to transparent route upgrade, this question, but I was speaking to a colleague about he was developing the asset management strategy in Saudi Arabia. So your example of sand displacement was really powerful.
Yes.
Has any of this information been incorporated into asset management plans elsewhere?
Just to understand, you mean about the sand accumulation? Yes. Actually, these examples have been applied to the Middle East region where they're suffering of that. So we have applied this in that region, and it works very, very well because you can detect it early on because it needs, I think, to reach a certain level for the rail to stop. So we identify automatically the location of the sand accumulation early on. So in that way, you can do that. Yeah, but yes, Saudi Arabia is a very good example. Yes.
Yeah, I was interested in the drainage one, where you showed where the drainage had failed. What sort of resolution size have you got on that? And how early can you detect sort of differences in ballast dust occurring from drainage failure? Okay, so the resolution, the spatial resolution, is determined from the source satellite data used. In the example I showed you, that's a 10-meter resolution, but it can be improved depending on the type of satellite data used. How early can you pick it up then? What sort of difference in refractive index will you start? What's the sort of difference you'll get? How early can you start to see degradation? We can detect it from, because we look at historical data, and so we have a baseline, and anything that is different to the baseline, it can be detected straight away with every satellite pass. So I would say quite early on. Because we're talking about surficial also soil moisture.
Thank you. Any other questions? That was a really fascinating perspective. Thank you very much.
Oh, I'm glad you found it. Thank you.